everyone. Firstly, I would like to thank the conference organizers for giving me an opportunity to present my latest results of my work. My name is Monika Michalska, and I am from Institute of Electronic Materials Technology from Warsaw, from Poland. I will tell you something about materials for lithium-ion batteries. So as you know, lithium-ion batteries have been used in many portable devices, such as mobile phones, digital cameras, laptops, iPhones, as well as hybrid electric vehicles, plug-in hybrid electric vehicles, owing to its high working voltage, high energy density, long life cycle, small dimensions and weight. And as you know, the battery consists of three basic elements: cathode, positive, anode, negative, and electrolyte. And I focus on cathode, and I choose the material lithium manganese oxide. This material is promising to lithium-ion batteries due to its low cost of preparation, non-toxic than, for example, lithium nickel oxide or lithium cobalt oxide. And this material is stable and has the theoretical capacity about 138 mAh per gram, and the practical capacity is between 110 to 120 mAh per gram. And the operating voltage is 4,1 versus metallic lithium plating. However, major drawback of this material is its poor stability with electrolyte and fast capacity degradation during cycling. So this is why I surface modified this material. Okay, so on this picture you can see the structure of stoichiometric lithium manganese oxide spinel, which can be described as a face-centered cubic closed package oxygen, in which lithium and manganese ions occupy tetrahedral 8 sites and octahedral 16 sites. And there are a lot of chemical synthesis of nanomaterials, as you know. For example, combustion, hydrothermal, solid-state reaction, microwave, but I synthesized the lithium manganese oxide powder using modified Sauger method. And here you can see the flowchart of Sauger synthesis. So in the first step, I dissolve in the ionic water separately lithium and manganese salts, then mixing and stirring, adding complexing agents, citric acid and acetic acid, and mixing and stirring. Next step is slow evaporation, drying at 150 degrees for a few hours in air and grind it in agar mortar, and here we'll obtain the preheated powder, so-called exerger. So this material, the exerger, is calcined in this temperature range for a few hours in air, and we obtain the single-phase nanocrystalline lithium manganese oxide. And here you can see the X-ray powder diffraction results, which were obtained for lithium manganese oxide synthesized by modified Sauger method. And the average particle size of the crystallites, which were calculated by the Shor equation, were between 20 to 30 nanometers, and there was no other impurities here. Okay, now you can see the morphology of lithium manganese oxide crystallites, which have a regular shape and good dispersivity, and the average size of grains is about 50 nanometers. Second step. So in first step we obtain nanocrystalline lithium manganese oxide powder, and now we surface modification. And now the step is a surface modification of these grains using ceramic coatings. How can we do it? So here you can see the flowchart of the low temperature chemical synthesis for the surface modification by ceramic oxides. And we use the ceramic oxides. It was cerium, zirconium and silicon dioxides, lanthanum and aluminium oxides, and it was 1% of amount. So In first step, we dissolve in alcohol medium ceramic oxide. Then we added the so-obtained nanocrystalline lithium manganese oxide to obtain the homogeneous suspension. We adding the polyvinyl alcohol, slow evaporation, and next step it's drying and heating and grinding in agate mortar. And the last step is heating at 350 degrees in air for a few hours. Okay, we do the X-ray powder diffraction for all surface modified with 1% of lithium manganese oxide, but we didn't observe the ceramic oxides because it was too small. We also do the Raman spectra of lithium manganese oxide with various ceramic coatings, and we didn't observe the ceramic oxides also. And you can see the relatively narrow lines half with circa about 50 centimeters, which allow to determine the crystallographic structure. And the strongest vibrating mode at 625 centimeters corresponds to a symmetric stretching vibration of manganese oxide bonds in manganese oxide groups, while the weaker side mode at 583 centimeters and a weak mode at 479 centimeters delivered from symmetric bending vibration of manganese oxide bonds. We also do the morphology studies, and you can see that surface modification with silicon dioxide in first. So we didn't observe the silicon dioxide. When we modified with zirconium dioxide, we observed the grains of this oxide, and the size of these grains were about 50 nanometers, and these grains agglomerates and have crystallite structure. Next oxide is lanthanum oxide. We can see also this material, and the average size of these grains were about 100 nanometers, and these grains have crystallite structure. Cerium dioxide we also observe on our studies, and the size of these grains were about 100 nanometers, and these grains agglomerate. And the last, with aluminium oxide, you can see that the size of these grains were about 100 nanometers. We also do the electrochemical tests. So the electrode system was 3 electrode, yeah? Positive lithium manganese oxide or lithium manganese oxide modified with ceramic oxides. Negative and reference electrode, it was lithium metallic. And the electrolyte was lithium hexafluorophosphate. So here you can see the charging and discharging profiles of pristine and surface modified lithium manganese oxide powder, nanopowders at 1C current range. And you can see that when we modify a surface modified with cerium dioxide and aluminium oxide, we obtain the best initial capacity. For cerium dioxide, we get 150, and for aluminium oxide, we obtain 111 milliampere-hours per gram. So it's good information for us. On this picture, you can see the specific discharge capacities of pristine and surface modified lithium manganese oxide powders, and it should be added that the cells have been discharged subsequently with a current range which varied from 1C to 30C, and the cells during last 25 cycles have been discharged at 1C current rate, and the charge current was 1C at every cycle. So you can see that the best specific discharge capacities we obtained for lithium manganese oxide, which were modified with aluminium oxide, and it was 109 milliampere-hours per gram, and 140 ISS2013, it was for lithium manganese oxide, which were modified with cerium dioxide. And there are electrochemical results. You can see the cyclability of pristine and surface modified lithium manganese oxide powders. And when we look, the best results we obtain when we surface modified this lithium manganese oxide with zirconium dioxide, cerium dioxide, and aluminium oxide. So here you can see in table the electrochemical results, and you can see that the best material which we chose, it was lithium manganese oxide with aluminium oxide and with cerium dioxide. And let's go to conclusions. So XRD results showed that the powders of lithium manganese oxide obtained by modified soldier method were single phase. Also, the cubic spinel structure has been proved after surface modification of lithium manganese oxide grains by ceramic oxide coatings. All the surface modified lithium manganese oxide powders with ceramic oxides have been shown the reduced specific capacity compared to lithium manganese oxide without surface modification. The results of electrochemical tests show better capacity retention due to coated layer on the surface of pristine lithium manganese oxide powder, and the best results we obtain when we and the best result for initial capacity we obtain when we modified lithium manganese oxide with cerium dioxide and aluminium dioxide. A reference. And I would like to thank for the scholarship which I awarded by the Mazovia Voivodeship Office. And this work was supported by the National Center for Research and Development. And thank you very much for your kind attention.
Thanks a lot. So, are there some questions? Yeah. I've got a few out of curiosity. The modified process with the Solgen method to prepare the oxide, lithium manganese oxide, how long does it take? Is it 1 day of work, or is it huge work? How long does it take to make the synthesis?
The synthesis about
the lithium manganese oxide, the first one you
2 days to obtain lithium manganese oxide. It's fast.
It's fast.
Yeah.
Okay. Yeah.
Okay, I can't hear. Maybe I'll come to you.
Can you avoid the temperature heating of the particles?
During when I surface modified, yes? About heating. It was my
Intuition? Or
yes, it was my intuition. But I would like to try any temperature. Yes?
Question? Yeah.
Okay, I just wanted to ask, how does this material compare with current lithium-ion batteries? Because what is the capacity of current lithium-ion batteries?
The capacity is for For example, for this material, yes, I will tell you on my first slide.
Yeah, it's about 150, the lead
Yes.
theoretical. And what about...
And the practical is 110 to 120.
And what
So
about...
for my lithium manganese oxide, it was 108. Yes, and when I modified this material, the capacity was higher.
Yes, but what about the current lithium-ion batteries? What is their capacity?
So are you battery better? Or?
Yes, I think it's better.
Have you patented it? Have you got a patent on that?
No, not yet.
So you are risking of distributing the information for free.
No.
What's it?
Okay, maybe last question back.
I have a small question about the stabilities of this material in comparison with other. I mean, time stability. You know that lithium-ion batteries, they are like segregate this time. So what about this material? Is it more stable than others, or is?
I think when we surface modify this material works longer than without modification.
Okay. So yeah, thanks again.